Hello guys, welcome to the first USACO video on my channel, and in this video we are going to be starting off with a very basic USACO problem, and in future videos we will do progressively harder problems or just more interesting problems. So this is from the 2015 December Contents Bronze, and so it's called fence painting, problem number 1. So just read it or read the problem first, you can pause the video. All right. If you didn't read it, I'll give you a gist of what's happening. So essentially, in this problem, we model the fence that John and Bessie are going to paint as a one-dimensional number line. And so what happens is that John, who's a painter, John the farmer, just paints a fence, I guess, picks any two arbitrary endpoints on this number line, and he calls his endpoints A to B. And essentially paints from A to B. And then Bessie the cow doesn't really care about his instructions because Bessie the cow is a phenomenal painter, but unfortunately she doesn't listen, right? So she arbitrarily picks maybe two endpoints and she calls it C and D. And then she paints from C and D. Our goal is to find the total amount of paint painted, right? And so the total amount of area that's painted. So the total amount of units that was painted across the fence. In this case, the total amount of units painted across the fence is just D minus A visually, right? We can go all the way to D, and then we have to obviously subtract A because this region is not painted obviously. So it's very obvious. But we realize that this is obviously not the only case. This is just a specified case, right? We could also have a case where um D is less than B. In this case, the answer would now be B minus A instead of D minus A for the total amount of paint covered. So essentially, the problem is dependent on where the overlap or the intersection is, and that intersection is dependent on where the coordinates are A, C, D, and B. And we claim for these coordinates to be one-dimensional, and by convention, one dimension usually talks about horizontal movement. That's why you see in the problem statement, it says x is equal to A and x is equal to B. It's just say that A and B are one-dimensional units, and one-dimensional units are usually horizontal by convention. So now we need to find, just some generalized formula to find the total amount of paint covered, and then we need to implement it, and I'll be using the language Java to do that. So basically, in general, we can say that the answer to this problem, right? So let's just say the answer to this problem. So the answer to the problem, which is we're trying to find the total amount of paint covered, is going to be B minus A plus my bad plus D minus C is going to equal, and then minus the intersection between these two segments. So the idea is that we can find the length of where John paints, and we can add it to the length of where Bessie paints, and then we can subtract the intersection to find the total amount of paint covered. And the reason why this is true is because think about it. B minus A contains the intersection, so it counts it once, and D minus C also contains the intersection again, so it counts it twice. And so if you only want to count it one time, we subtract 1 because we have 2 counts and we only want 1 count, so we just subtract 1 to only have 1 count, and then we avoid the overcount. So that's why this formula checks out. But now we need to find the intersection in terms of B, A, D, and C, right? B, A, D, and C. And also realize that these inequalities hold in our problem. We have A will always be less than B, and D and C will always be less than D. The reason for this is by convention A comes before B, and C also becomes before D, and we claim to be working with obviously positive integers or non-negative integers from 0 to 100. So that's why we have these inequalities. And also, like, just look at the test cases in general. Look at the test cases in general, right? You always see that this is 7 is A, 10 is B, 4 is C, 8 is D. So, like, we're guaranteed by the test cases for D to always be greater than C, obviously. So then we just need to find how to do the intersection in terms of these things, right? So to do that, let's just have a scenario. Let's just make a scenario for the intersection. So say we have, oops, I need to, bruh, okay. So say we have a number line again, right? This is one-dimensional number line. Say that the intersection starts from x to x plus k, because we realize that these are just measured in x units or horizontal units. That's really what the constants a, b, and c, d are measured in. So let's claim that the intersection is this, from x to x plus k. So really the intersection is equal to k in this case. So if that is true, then we know that we're going to have red, I'm drawing red, and we're also going to have blue. So we're going to have both colors essentially mixed in because it's the intersection. It's where the two colors overlap. So then we note that, I think I used blue for B and A, right? So then we note that A is the first endpoint that John has to place down. And if that's true, then A has to be either X or less. Because if A is like starts over here, then the blue segment has to start over here. But we observe that the blue segment um, starts over here, or it could start over here, right? If it started over here, right, then it would not change the intersection, right? We would just extend the length, but the intersection is still preserved. If A lies within X, if A lies between X and X plus K, then we know that the blue segment now starts over here, like right here, for example, and this blue segment over here is no longer there, and it's gonna start from here and then just go until it reaches B. But the idea is that the intersection is not preserved if it lies between x and x plus k. And so if we want to preserve the intersection to be k, we have to make sure that it's x or less. So A is x or less. And the same thing for C, because C is the first endpoint that, in fact, I guess let's do this in red. C is the first endpoint that Bessie is going to place down. And we know that it has to be x or less. If it lies within x and x plus k, then the intersection is not preserved. So let me just redo these things. So we could have C maybe be over here. So then we note that essentially then we note that after this is true, after you place the two endpoints, in fact, let me just do this in another color. So this is going to be C. So after we place the first two endpoints, let's just go back about placing B. So B is the last endpoint that John's going to place. And we know that John has to place it on x plus k or more. So she has to place it in that region. The reason for this, so we observe that B has to be greater than or equal to x plus k. The reason for this is literally just the same thing, right? If B is less than x plus k, then this blue segment, well, let's say B is over here, right? If B was over here, right, less than x plus k, then the segment would just stop over here. And this part of the intersection that we want to preserve will now be gone because it only has red, so it's not a part of the intersection. So essentially, we are shortening the intersection or just not preserving it. So in order to preserve the intersection, we have to make B greater than or equal to x plus k, and this follows for D because D is also the last endpoint that Bessie will place. So then we also note that D has to be greater than or equal to x plus k. Now, here is the tricky part into this, I guess. So let me fix the thing. Hold up. Ooh, okay, so this is this. Not so. Let me have blue here. So we observe that these statements have to be true. The underlined statements, these statements have to be true. Okay, just so you know that. Now here's a tricky part. We need to find a way to extrude K, or not, let me not say extrude, to extract K. Because remember, the intersection is K. So essentially, we're just trying to find how do we make a K out of all these constants. One thing we can do is we notice that one of A or C has to be X. One of them have to be X. The idea is that if we choose A and C to be over here, right? like if I choose, let's say we have the scenario, right? If I choose A and C to be there, right? If I choose A and C to be there, then we have this, and then we have this. Essentially, the intersection is not preserved because from C to X, we have a new part of the intersection. So we know that at least either A or C has to be X, right? If C is here, then we preserve the intersection. If C is over here, now we preserve the intersection because it starts from there. And then obviously we don't really care. A just goes from here, but it doesn't intersect anything. So A or C has to be X. And we know that X is the maximum of any of them. So if X is the maximum, what we do is that since we know that A or C have to be X, we just take the maximum value. So we just take the maximum value of A and C to get X. And then we know that this can be subtracted from the minimum value of B and C. So let me I'll just do it in blue, it doesn't really matter. So it has to be subtracted from the minimum value of B and C. And the reason for this, or B and D, my bad. And the reason for this is because we note that if one of A or C have to be X, right, to preserve the intersection, then one of B and D also have to be X, because I have to be X plus K. I mean, either one of B or D have to be X plus K, because think about it, if both of them were like just more than X plus K, then we know that the intersection is just going to be lengthened. It's going to be more, so the intersection will be preserved. So in order to make one of them, in order to preserve the intersection, we have to make one of them X plus K, and we know the minimum value is going to be X plus K. So essentially we have to print out the minimum value of B and D because we know that one of them is going to be X plus K and one of them obviously has to be more. So we just have to print out the minimum value in order to get that. And once we do that, we get X plus K minus X, and we get the intersection. So essentially we get K back, which is what we want. So we get K back. So all we notice is that the intersection is X plus K minus X, and then we saw how do we get X plus K minus X from these constants. So now we can finally implement the problem, because now we know that that this intersection over here, this little nonsense, this is essentially equal to the minimum value of A and B, or B and D, minus the maximum value of A and C. So now we can implement this into Java because this equals the total amount of paint covered. So let's do this. I've already imported the packages needed. Call the public class fence painting. Don't really worry about this nonsense over here. Because yeah, just don't worry about it. So then first thing we're gonna do is buffered reader equals b art equals noob buffer reader, then new file reader, and then it's just gonna be paint.in. Okay. Oop, that's the car symbol. We actually need two, bruh. Okay, so then we're gonna do print writer. I'm just gonna use print writer w equals new print writer new writer paint.out. By the way, you can get the input and output formats over here. Okay. Now, essentially what we need to do is I'm going to claim that the intersection, so in intersection, we claim for this to equal, math dot minimum of B and D, so math dot minimum of B and D minus math dot maximum of A and C, math dot maximum of A and C. Then we claim for int total paint. So let's say total paint covered, total paint, right? That's our answer, the total paint. So the total paint covered is going to be D minus A. And then we said D minus C, right? This should plus D minus C. Minus C. Also, I forgot I have to put the inputs. My bad. I'll do the I'll do the inputs later. Don't worry. I'll do the inputs later. Like I'll just do the inputs later. Sometimes I just don't worry about the inputs. I have to. I'll have to take the inputs. Right now, I'm just getting the good chunk of the code. So we have it's B minus A, D minus C, and then also we notice that no, we have to subtract the intersection, but we know that the intersection could be 0. So in the case that it's 0, we want to make sure that we know that like okay, so basically we know that this expression could very well be negative, right? If there's no intersection, then this is going to be like some sort of negative value because we know that it's not going to be positive, right? Because there's no intersection, so there's no way there can be a positive intersection. That means it could be like 0 or it could be negative. So we just need to ensure that our code prints out 0 if this does not converge to a positive integer, because if it does not converge, that means there's no intersection. So you just make sure that when Java computes its expression and gets a negative, it prints out 0 because that means there's just no intersection. So we'll do math.maximum intersection comma 0. All right, so we'll do math.maximum comma 0, and then we want to print out so pre dot print line total paint, and then we want to close this, so pw.close, and then let's actually take in the inputs now. So we need a string tokenizer, by the way, so string tokenizer st equals new string tokenizer br.read line. Then we want integer a to equal equal bruh. Oh, bro, I almost forgot how to do Java. Dot parse int. Oh, you have to capitalize, bro. Draw. St dot next token, right? Okay. Then we could just copy this for B. And then I'm gonna copy this for the C and D. But I'm gonna actually make a new string tokenizer first for the different so new string tokenizer your read line the C and D, and then we note that boom. Why is this nonsense not? Okay, it should be. Let me just refresh this, I guess. Like, it literally should be working now. Because I just finally made the inputs. Okay, perfect. So now let's just check our code to make sure that everything is right, because I just want to make sure that I implement it right. So we inputted our 2 packages, right? And then we essentially did buffer reader and then print writer, and then we made our string tokenizer for A and B, and then we made it separate for C and D. We know that we're guaranteed for D to be greater and C to be greater and B to be greater than A. Oh, we're guaranteed for D to be greater than C and B to be greater than A. And I don't know why this is. Oh, throws IOE, bruh, throws IOE exception. Dude, literally, who cares about IOE exception, bro? Okay, I forgot that nonsense. Okay, throws IOE exception. It should work now. Sometimes I just have to refresh it because Riplet is very slow. I gotta make sure. I just want to make sure I implemented this right. Yeah. So we almost forgot throws IOE exception. You also have to put that there. So we have this nonsense. We put string tokenizer. We entered A and B. Looks good. Then we said intersection is equal to math.min BD. And then we have AC, then total paint, B minus A, D minus C. Then we know that it could be 0, so we just print out 0. And then print out total paint and PW close. These brackets look good, and we just download the file now. So download, I've already implemented like other versions and like just tested it to make sure that I'm not flooding. So Java, I'm gonna submit my solution. So choose file. I need fence painting. Not worry about those other files. Those are like my dad's. Okay, so submit this nonsense. Dude, it better work. Like, if it does not work, then dude, I should not have a compiler error. Okay, good. All right, let's go. So, yeah, guys, that is how you do fence painting. And we'll be doing a harder problem in the next video. That's essentially just a two-dimensional version of this. You probably already know it. You probably already know what problem I'm gonna do in the next video. But yeah, stay tuned for the next episode. Let's go.